Papa Flammy's Advent Calendar.
Here. Good morning, fellow mathematicians. Welcome back today, numero 4. If you are still looking for a great wooden gift for your loved ones, check out betonundholz.de, my website for handcrafted woodworking stuff. If you live outside of Germany, shoot me a mail to this mail right here and we can get in touch. Now, I'm pretty certain that basically all of you have heard about that there are not only circular wheels that can drive smoothly over a certain path. No, there are also square wheels, gear-shaped wheels, and so on. For basically every curve you can think of, there's a certain road that you can design such that you can ride smoothly. And today we are going to take a look at one of these structures, namely square wheels. And it's going to be quite surprising what the result is going to yield. So at first, here's a little demonstration of what a square wheel looks like. And you are going to notice in this demonstration that the square wheel is going to drive over a pretty bumpy road. And if you take a look at just the road, it looks like it's rolling over some kind of circular path in a smooth manner. But it's more surprising than that. The answer is seriously unexpected and leads us down a huge rabbit hole that we will take more of a look at in the next videos. And we basically laid the groundwork back when we talked about foci of parabolas and the like. So it's going to be really exciting. So definitely watch until the end of the video. And if I reference any other video, link down in the description also to the Advent Calendar playlist. And now we are going to dive right in. Now, we don't know what the shape of the road is going to be, but before we get started with something, we need to clarify what a smooth ride actually is. For this, I'm going to leave out that we need to have a constant angular velocity. So this is something that only holds for circular wheels. This is why we like to use them. But there are other conditions for a smooth ride that we need to lay out. And one of the biggest conditions is that our wheel, so the square, is always tangent to our road when it touches it. This is one of the things that we need to have. And I'm going to put the conditions here. I'm not going to write them out separately. Now, also what we need is, if you drive with a car, you're going to notice that you are not going to wiggle up and down at all times. And if you take a look at the demonstration once again, at the video, you're going to notice that the center point of the square is always staying constant on the x-axis. And this is what we want to have. We want the center of our wheel to be always at a constant height. Those are the two conditions that are needed for us to have kind of a smooth ride, apart from the angular velocity stuff. So I'm going to write it out a tiny little bit, or I'm going to sketch out the scenario a tiny little bit. So let's just imagine that our square right now is in this position right here, with a center of the square here, a side length of a of the square. And also what we want to have is, if we do a projection downwards, it's always going to be one height y at all times. What we need is we need to have a constant height at all times. I'm going to project our x-axis on here. And this right here is, for example, just a y length. Okay, this is what we need. Now, what we also need is our road. And how is our road defined? Our road is defined in such a way that the point of contact, which is exactly this part where our height y touches exactly our road, is tangent. So this line segment, our wheel, is tangent to the road, just like this. So a, in this case, is a linear function, and a special one at that. A is a tangent to this road, okay, that we are going to find an equation for. Okay, so the first part is done. This is our whole sketch, and now we are going to play around with the sketch a tiny little bit more. And what I'm going to do is I'm going to project a little right triangle into here, and we're going to make use of similar triangles to basically turn this into a differential equation. Now, if I project half of the side length on here in a right angle, this right here is going to be a over 2. Then this is going to turn into a right triangle. Now, the cool thing about this right triangle is that the side length y, that we don't know what it is because the y depends on the position that we have at all times. It's going to change over time, obviously, because our wheel is going to roll around. But this height right here overall, so basically I phrased it in the wrong way, that the center needs to stay at the same height at all times, and y is going to vary over time. I did a little oopsie there in my formulation. Language barrier, ha, I can be excused, I'm a German fella. But overall, point is, the cool thing about y right here is that it's parallel to our y-axis. And that also means if we now put the slope triangle into here for our linear function a or our tangent a, we can do some nice trigonometry at that. This right here is going to be a right triangle once again. And now let us just take a look at the angles a tiny bit. Now let's just say our tangent A is going to rise with a certain angle phi. Now, we in a former video, namely last video, have found out that if we have a linear function and it rises in an angle phi, then that linear function has a slope of tangent of phi. This right here is the slope of each and every linear function. Now, how can we use this fact? Well, the cool thing about the tangent of phi is that it's also defined by the opposite over the adjacent. Now, that's the cool thing about linear functions, namely the opposite is nothing other than the change in y, and the adjacent is nothing other than the change in x. Now, if we just take a look at an infinitesimally small change, then our normally delta y and delta x are going to turn into dy and dx. As always with differential equations, we just want to take a look at very, very small changes. This is what we want to do. So overall, our change in the angle phi, you could say, is nothing other than dy dx. It's the change in our height y at all times. Now this right here is already a differential equation that we could solve. But it sucks a tiny little bit because we have no idea what the tangent of phi actually is. And we are going to deal with this. Because if we now take a look at what we got right here, I'm going to draw it out once again. You are going to notice something very cool. Namely, since this side length right here, our run, is parallel to our x-axis and this side length y is parallel to our y-axis, that means that this right here encloses a right angle. Now this right here is our angle phi. This was also a right angle. Now, what you're going to notice is if this angle right here is, for example, alpha, then phi plus alpha is going to make up pi overall, or 90 degrees, because this part right here is already 90 degrees and the interior angles add up to 180. Now, this overall angle is 90 degrees, but one part of it is already phi. This right here is also a right triangle, meaning by just sorting out the angles, we are going to notice that 90 degrees is equal to phi plus alpha, meaning alpha plus phi right here must be equal to those 90 degrees. Meaning overall, those two triangles are actually similar, and we get an angle phi here. And this is very cool because we have in the connection now. Because now phi is also connected to this triangle by the relationship of cosine. Namely, the cosine of phi is equal to adjacent over hypotenuse. So a over 2 over y is a over 2y. Okay, very nice. Now we can try to connect those, and the tangent can be expressed solely by sines and cosines in and of itself. Because if we take a look at the tangent of phi, it's the same as sine divided by the cosine of phi. Now what I'm going to do here, this makes our spiel a tiny little bit easier. I'm going to square both sides. And why am I doing this? Because of fundamental theorem of trigonometry. Namely, we all know that the sine squared plus the cosine squared is nothing other than 1. Meaning we can replace our sine squared by 1 minus the cosine squared. So this right here is the same as 1 minus the cosine squared divided by the cosine squared. Or in other words, we can say that the tangent squared is nothing other than, if we track this out, 1 divided by the cosine squared minus cosine squared over cosine squared is 1. And if we now take the square root on both sides, we actually get an expression for our differential. Namely, we get that dy dx, which is nothing other than the tangent of phi, is equal to the square root of 1 over cosine squared. I'm going to write it out. Minus 1. This is what we got right now. Obviously, plus minus, but this is just a matter of family of solutions for differential equations. So I'm going to leave it out for now. We are going to talk about the solution which makes sense at the very end. Now, 1 over the cosine, but squared. We know what the cosine of phi is. That is a over 2y. Or if we replace this by 1 over the cosine, this just is the reciprocal. So 2y divided by a, but squared. And this right here is a differential equation that we can now solve. And this differential equation gives us the path for which our square is going to roll over very smoothly. Very much so. Now, we just do separation of variables. We are going to divide both sides by the square root term here, leaving us overall that 1 over the square root of all that we got right here, dy dx, is equal to 1. And now we are going to integrate both sides with respect to x, meaning our differentials are going to cancel out. And on the right-hand side, we just have the integral of dx, giving us overall that the integral of dy divided by the square root of 2y divided by a squared minus 1 is equal to the integral of dx, which is nothing other than x plus c, obviously. And now we can go ahead and start to solve this integral right here. And if you're a sneaky guy, you already know the solutions to this. But we are going to do it step by step because we are on Papa Flammy's channel here and I love doing stuff step by step. So the first thing that we are going to do is we're going to get rid of this part right here, because under square roots and squares and minus and plus ones mostly hide something trigonometric or hyperbolic. And this is what we want to try to take out of this integral right here. So at first we are going to say let I don't know I don't really care. No, a is stupid. U. We are going to do a u substitution here. U be equal to this part right here. 2 divided by a times y. I didn't use a obviously because we have an a here. That would be fucking stupid. Now, if we were to differentiate both sides implicitly and multiplying both sides by a over 2, it's not equal to 0 because a is non-zero, otherwise you would have a very shitty square wheel. We are going to get that a over 2 du is nothing other than dy. By plugging all of this in, what we are going to get for now is the integral of, and we substitute the dy for this. Our differential du is going to stay here. By the linearity of the integral, we can bring the a over 2 to the outside. So let's just clean it up a tiny little bit. Square root of u squared minus 1 is equal to x plus c. And now we can just go ahead. This is already so much easier. And for this, we could use, for example, trig substitutions. And this right here screams, for example, for the fundamental theorem of trigonometry. You could kind of use this part right here. So you could see that cosine squared minus 1 is equal to negative sine squared, but that would be shitty because we would get an imaginary root. You could use the tangent identity of this part or the secant identity, but we are going to go a different path here and we are going to use hyperbolic substitutions because it makes our life way easier. There is a similar theorem for hyperbolic functions, and the theorem is known to be it doesn't have a name, the fundamental theorem of hyperbolicism. I don't know. It really doesn't have a name probably, but as a matter of fact, we have covered it here on this channel before many times, and I think I derived it way back in the days. We know that the hyperbolic cosine squared minus the hyperbolic sine squared is equal to 1. That's the relationship right here. And how are those similar? Well, if we were to add the sinh squared on both sides and subtract 1, we could use a substitution of u being equal to the cosh to get ourselves the square root of the sinh squared, which is nothing other than the absolute value of sinh, but we don't care about the absolute values here because we don't know the domain over which we integrate off, so we just leave it out. And we have left out our plus minus before, so this also gets rid of the argumentation a tiny little bit. What we are going to do is we are going to introduce substitution, namely, let cosh of t be equal to u. That's our variable under the square root. Now, if we were to implicitly differentiate that, we are going to get that u is nothing other than, and the differential of cos is kind of similar to the differential of the cosine, but here we don't get a negative sign. This just turns into the sinh of t. And we can plug all of this in. This right here is going to give us that x plus c is nothing other than the integral of, and now the u is sinh of t. I forgot the differential 1 operator, dt over here, divided by the square root of, and now we plug for u our cos in, so we are going to get the cos squared of t minus 1. And just what we talked about a second ago, and I forgot the a over 2, let's put it right here. There was the constant in front. Cos squared minus 1 by the fundamental theorem of hyperbolicism. We are going to get that this is nothing other than the sinh squared. And this is what I blabbered about before. This right here is the sinh squared, but the square root of the sinh squared is nothing other than the f sub a, or just the sinh in and of itself. So this right here is going to turn into sinh over sinh, which nicely is nothing other than 1. So we are going to integrate the differential 1 operator dt, turning this into a over 2 times t. And now we can just resubstitute everything. We can take the inverse hyperbolic cos right here, the hyperbolic cos. There was a pleonasm. It was doppelt gemoppelt. I was using the same term to describe itself. That was stupid. So we are going to use the area hyperbolic cosine on both sides, giving us that t is nothing other than cos of u, or cos of u. So x plus c is equal to a over 2 times the arc cos of u, but we also know what u is. That was our very first substitution. Namely, u is 2 over a times y. So this right here is a over 2 times the inverse cos of a over 2. No, 2 over a. 2 over a, yeah. 2 over a times y. Now we can just solve this for y, and then we are done. And this leaves us with a very interesting curve, which is indeed not a circular path. What we are going to do is we multiply both sides by 2 over a. So we get that the inverse cos of 2 over a times y is nothing other than 2 over a times x plus c. By applying the cos on both sides, we are going to get that 2 over a times y is equal to the hyperbolic cosine of 2 over a times x plus c. And now what we are going to do is we are going to multiply both sides by a over 2. It's not equal to 0. We are going to get that y of x, the path which describes our road that we can bump over, is equal to a divided by 2 times the hyperbolic cosine of 2 divided by a times x plus c. And this right here is an incredibly famous solution to a differential equation. And maybe you have heard of it before. It's the path that is gonna be traced out by a hanging chain, for example, or something just hanging down. Do I have a cable? Just imagine I have a cable. If I let it hang down, it kind of looks like a parabola, but it actually isn't a parabola. I mean, to a certain extent, it is a parabola, but just approximated, because the cos includes something of magnitude x squared, but just approximately. But overall, this right here is a so-called catenary curve. And we need to add something for it to actually be the path that our square rolls over. We just need to add a sneaky little negative sign. That's the physical argumentation here, because otherwise our road would look like this and you would need to write on it upside down. The solution to our problem is the so-called inverse catenary curve. And if we stack such inverse catenaries to one another, we are going to get the road where our square wheel is going to move over very, very much smoothly so. And it's a cool curve. And next time we are going to use this formula, like the generalized formula is just with an a here and 1 over a here, but this is the solution to our problem with the square overall. But other than that, we are going to use this to solve something completely different than talking about a square wheel running over a certain path. So this right here is seriously surprising, and I hope you did enjoy what you have seen today. I love it. I love the solution, and it's so extremely unexpected. You wouldn't think that hyperbolic cosine pops out when it comes to a square rolling over a few bumps. Hope you did enjoy what you've seen today. This has been day 4, and I would love to see you on day 5 of the Advent calendar. And up until next video, I wish you guys a flammable day. See ya.